Hi, this is Mark Evans, and I'd like to show you a couple of tiny little programs that I wrote for my qualifying exams called inFormant and Timbreland. If you download these from my website, they'll come as a zip file, and of course you can double-click on that and get the application out of it. The first time that you try to run the application, you'll probably run into a dialog box saying that it can't be opened because it's from an unidentified developer. The way you get around this is by right-clicking and saying Open, and then when the dialog pops up, selecting Open again. Both of these programs use SuperCollider for sound synthesis. There's a copy of SuperCollider running inside the application package, and SuperCollider takes a few seconds to start up. Once it gets going, you'll be presented with a diagram created by my teacher, Clarence Barlow, which has all of the different vowels that we produce as human beings on the right, and on the left a bunch of symbols that Clarence created for vowels that are impossible to produce with the vocal tract. If you know Clarence, strange symbols and nomenclature are no surprise. On the axes, we have the frequencies of the first two vocal formants. In case you're unfamiliar with formants, I'll explain briefly the mechanics of vowel production. When we produce a vowel, our vocal folds produce a pitched, buzzy sound made up of hundreds of brief, so-called glottal impulses. This sound is then filtered by the chambers of the oral and nasal cavities, the configuration of which can be manipulated by the tongue. Just like different-sized PVC tubes resonate at different pitches, different-sized chambers in the vocal tract cause a boost in particular frequencies. The frequencies that are boosted are called formants and are crucial to the perception of speech. There are many formants, but it turns out that the lowest two are particularly important, which is why they occupy our X and Y axes. In this program, the bright, buzzy sound of the vocal folds is simulated with a low-pass filter's saw wave. Two resonating filters then simulate the formants. The fun of the program is that you can click or drag anywhere, and it'll produce a simulated vowel using the formant frequencies at the coordinates you click. On the left-hand side, you can try your hand at impossible vowels that, as Clarence says, are only technologically realizable. And if you want, you can change pitch by scrolling up and down with the mouse. Admittedly, in this video, you can't really see me doing that. So that's inFormant. It's a simple program, but kind of fun to play with. The second program I'd like to show you is called Timbreland. This diagram is adapted from a paper by Carol Krumhansl in the late 1980s. The research in question used a process called multidimensional scaling to discover three important dimensions of timbre. How bright a sound is, that is where the spectral centroid is, the length of the sound's attack, and the amount of spectral flux, which means how quickly the spectrum is changing over time. In the original research, test tones were created using some form of FM synthesis. I couldn't really find any details on how they did it, so instead I created the tones using additive synthesis, which is to say adding up a harmonic spectrum of sine waves, weighted according to the brightness. For spectral flux, I modulated the amplitude of the different sine waves in the spectrum, and for attack time, of course, I imposed an envelope. We can click around in various spots to hear what it sounds like. You can change the depth of the plane by scrolling. I would say that this program is fairly convincing evidence of the inadequacy of a three-dimensional conception of timbre. There's clearly a lot more going on in the first milliseconds of a tone than a simple envelope can convey. Also, there's nothing in here to represent the spectra of instruments like a clarinet, in which only odd harmonics are present. Still, maybe you'll have a little fun playing with it, and I do think that these dimensions have some bearing on timbre. They're just far from complete. Okay, so that's it. If you're interested in reading the original paper by Krumhansl, I'll link to that in the description. Also, if you're interested in learning more about Clarence's wacky ideas about music, I'll include a link to his book, Music Quantics. Thanks for watching.